Church has gotten ready, so please move up in the pews. I don't talk about these this is my third time presenting. And Rory, I think you mentioned something the other day, you don't want to get stale. So I promise it won't get stale, but there will be a little bit of review from last year. Marcia, thank you and your team and the Institute for hosting this and allowing me for that. I thank EPA, both in Region 10 that started work in acid mine drainage, and here also River Stakeholders Group, the state, and of course the BLM. They've all been really helpful in opening up to let us get access to acid mine drainage. So before I go any further, how many people collected water samples? Raise your hand. Keep them up if you collected them but had sulfide in it. You're analyzing the sulfides. Those that analyze the sulfide, what's the preservative?
Sodium hydroxide.
pH up, keep it up, because you don't want it to acidify or to neutral because sulfides broken down. I cut my teeth on sulfide back in the Midwest, Chicago, and Detroit, industrial processing, steel, plating, wastewater treatment. They have something called total sulfide, reactive sulfide, which is also defined under RECRA, or metal sulfide. A metal sulfide is a sulfide that can be destroyed by, for example, bleach. We use that with cyanide as well, see if it's a metal. So if sulfide can be destroyed, it's not going to generate acid. So I look at the tetrahedral I saw earlier, and everybody talking about removing parts of the AMD or ARD drainage system. That's the big answer right there. You got sulfide, you got oxygen, and bacteria. So what we're going to see today is, let me back up a little bit. The project that we're going to talk about is technology that takes solids from our food systems so they can use new products. Back in 2014, we were working with electricity to treat acid mine drainage. We started out in Bunker Hill mines of mining complex in the L complex. We worked with Bunker Hill mine, we worked with Southern Walls work, and we were able to get great reduction in metals and treated acidity. We got it down to parts per billion level. And if you want to look at one of the earlier presentations from here, so I'm not going to go into that too much. But we were looking back into the total solutions for actively drainage systems. One is treat acidity, remove heavy metals, and then what do you do with the solids? So the idea is, if you've got solids, they're going to have sulfides unless you destroy it, or bacteria is going to be or oxygen. So the problems with taking a solid material that comes out of a water treatment plant, or a flotation pond, or a tailings pile, is that it typically has sulfides in it, bacteria, because the bacteria probably haven't eaten all the sulfides yet, or they're still going, and the sulfide hasn't been destroyed. In ore material or related materials, or in water treatment systems that use alkalinity, high pH, and don't oxidize or destroy the sulfide, it's still going to be there. You have sulfide-bearing ores that are still in their residuals, other pyrotic materials. There's a giant mining company that's owned by the largest in the world for iron. They had a major dam failure back in January. 250-some people were killed. And the information that's coming out of there is that they use ore materials, so sulfide, to build their tailings dam. I believe we saw one that was 100 meters tall in Chile this morning, earlier today. Well, that dam was used to hold acidic drainage. It was iron, pyrotic material. And basically that water moved through the dam and destroyed sulfides and bacteria and around particle size. And geotechnical engineers will tell you that particle rounds, they don't go out, there's no, no angularity, and then that was dissolved, and it was the strength. So the idea of destroying sulfides so you don't generate acidic material is really important. We were playing with some of that material to destroy the sulfides and plant metals in some of that material. I was going to bring that data in here, but under IT issues I couldn't, so the data I have today is a little bit limited. So So the next thing we did is we looked at the technology we talked about last year. It's called MBT. It's a reagent system that ties up heavy metals in low to neutral pH ranges. We don't require hydroxide. As a matter of fact, we discourage hydroxide. And we tie up the solubility so it can stay stable in leaching conditions, not just solubility, but leaching conditions, whether it be acid mine drainage, acid rock drainage, TCLP, synthetic leachate, landfills, or acid rain. The other thing we did, again, getting to the construction material period piece, is we found that when there are large particles, and most geotechnical engineers will tell you that to get strength in concrete, you need particle support in them because the liner, the cement, and the fine drainage won't hold it together very well. It can if you know how cement works with it. So we overcame some of these problems of turning mine waste into a production or construction type material. We addressed the sulfide problem, we addressed the pH problem, and we got a strong liner system that's stable to pH changes, and the product won't leach metals. So we have two technologies. One is the MBT, which just basically addresses leachability of heavy metals. And tailings, wastewater treatment sludge, lime sludge, whatever it is, it'll tie the metals up so they don't leach. Both Recra, Circula, and other metals that usually fall into water quality objectives. We took that technology and we made it so we could generate strength out of paper materials. Those of you that are familiar with lime and water treatment know that metals have different pH points where the solubility is the lowest. And the problem with the lime system is, unless you get 2 or 3 pH points, depending on the metal in there, there's always going to be some metals that are going to be soluble and carry that out, so you won't hit your CPB level. So that's a problem with lime. Second, at that pH, sulfides are preserved. They're not going to go away. So in the MBT process, again, we don't use lime. This is our being a metal or hydroxide. This is solubility products. And they're out of the lab. They're laboratory analytical grade reagents. You'll see that the lower the number in the exponent, the lower the solubility. So if you look at the key metals here, as a hydroxide, you'll see that their solubility product is quite a bit higher than what it is for the MBT reagents. And that's critical because MBT stays stable regardless of pH. It's not a hydroxide-driven system, whereas the hydroxide, such as cement, lime, killdust, other pozzolan, are hydroxide-driven. So if that hydroxide is neutralized, it becomes acidic, the metals are released. And from a strength perspective, the strength falls over. So our system, we work in this pH range. We don't care where it is in here. If it's important, we can adjust it so it fits in there. When you get into low 4s, even if you had 7 3, which is pretty good, we've been able to tie up heavy metals so we don't leach into TCLP, SPLP acid rain, or a long-term extraction test called is method 1320, which is a multiple extraction procedure. And we tried this on some lime solids, and Kerry, if you're here, thank you for providing this a couple of years ago. We did a full-scale pilot study for water treatment and some lime solids about this time 2 years ago. The multiple extraction procedure is a series of 10 sequential extractions. You do one, you analyze the metals in that fluid, you take those solids from that extraction, move it down again, and you do that 10 times and look at the metals in each of those extractions. And that's roughly a 1,000-year model of stability. What we did is we wanted to get more real time. We substituted the lab grade reagent, which was basically acid rain. We used acid mine drainage from the American tunnel and the acid mine drainage, which was basically cement creek. And we applied it to our treated lime solids and untreated lime solids. So down here, in the lime solids, you can see what the total metals were in those solids. 60,000 per little group of pH is 8. Cat was pretty low, lime was way up. That's cobalt, copper, manganese, and zinc. And if you look up here, these are the pHs of the two fluids we use, American Tunnel and Cement Creek. And just see that those numbers, just remember those numbers in your mind, because we use those fluids as the extraction fluid on this material that was untreated, and then after treatment with MBT. So the first set of data, we'll go through real quick, I'll explain what happens here. This is American Tunnel on both untreated and MBT-treated lime solids. So, if you went back to that slide before, this 4.61 is milligrams per liter of aluminum in American Tunnel fluid that had a pH of about, I think it was 3 something. We ran through each of these 10 extractions for the treated lime solids and the untreated lime solids. Both materials stayed fairly stable through the fourth extraction. At the fifth extraction, we started seeing aluminum breaking out in the lime solids. And in the MBT-treated solids, the material, not only was it, and I should have changed it, it should be below detection limit, it brought the metals out of the fluid that were brought to it by the extraction. So we used American Tunnel, which had 4.61 milligrams per liter aluminum in it. We actually absorbed that, treated it, and it got incorporated into our treated metals. So each of these sequential extractions. So this material is extracted and moved to this one, to this one, to this one. And each of these had fresh fluid put out. So that's what that means. I'll go quick here. That was cobalt. You see the same patterns. Copper. Manganese. Zinc. And then we switched to Cement Creek water, which had a pH of almost 4, but not quite 3.9. And we did the same testing. We used the lime solids, and the lime solids were treated with the MBT. And you can see again that over time the lime solids started leaching, and the MBT-treated solids brought the metals out of the fluid that we contacted. And I'm just going to go quickly with manganese and zinc. And I should also note that in some of the data that we looked at, we met in our leachate, we met even with this level of water coming in, we met Colorado TBS for acute and chronic toxicity. So for MBT, I'll go for that quick. It doesn't use hydroxide, it ties it up, and I can move on from that. So what we want to do now is take this sludge we generated. We wanted to get strength out of it. We were talking last time about putting this material back in a mine somewhere where it could be used to seal the mine up, maybe slow drainage down, or fill up some of the cavities and find a place as a repository where it could be out of the way and low cost and provide a benefit for slowing down acid mine drainage or sealing mine or whatever. But we had some questions about strength and stability, and we had this thing happen in South America. So this is the third part of what we've done. So we took some of the lime solids, which basically calcium hydroxide polymer, and then calcium oxide. And then we took, this is the water treatment technology we use, which is advanced neutralization. I'm not going to go into that too much, but that's what uses electricity to treat acidity and remove metals. And it doesn't use conventional water treatment reagents like chloride, lime, polymer, alum, things like that. It takes advantage of the metals that are in the water, or chemistry and electricity over inducements to make it work. And we'll let dry chin out some of we'll keep it there. So we took that material, and then we also took the tailings cells. We ran through a series of studies. So this is from Gold Mine. Another field study. We were hoping to get a lot of cells generated to do some of the original work, but we didn't have enough, so we brought buckets of water back. And then this past summer, we actually got more material. This is where we started our field trial. Okay, Carrie, these will pick on you a little more here. These are your lime solids right here. And the first thing we did is just use conventional type 1, type 2 Portland cement at a couple of different doses. We formed 8 or 4-inch diameter strength test cylinders, pack them down, send them to a test lab and see where they break. And then we took that same material, the MBT treatment, with our strength enhancement in it. And this is material right here that was our first effort to see how we would do with strength. And it probably, and I think it got about 30 psi after 7 days. This one got quite a bit higher, and I'll show what happened. So, with plain lime salt, the type 1 and type 2, we ran 2 studies, one with a 20% and 35% dose rate. Both cylinders broke during the stripping of the casing, and so we couldn't do a 28-day, and we couldn't calculate a 28-day. Again, the other thing is we were limited to our funding, of course. We're self-funded, and the other thing is the amount of material we have to work with. I mean, start pounding cylinders, we use that material pretty quick. Then we took the lime solids and we added a 20% dose of the MBT with the strengthener in it, added a 20%. And the 7-day, as you saw in the previous slide, in one of them, 7-day, 30 psi, and 28 days, 120. Still not very good. And that would have been this one right here. Then we took this one right here, that was the one, and that was actually a blend of lime solids with kidney tailings at a ratio of 50 to 50. And we used a dose rate of the MBT-ES, and we got in 7 days, 1,760 psi, 2,360 in 28 days. So that shows that there's some strength. We just took some guessing at ratios. We can change the ratios and dosing here to get higher or lower strength. We can add more aggregate. Again, if you look at tailings, it's pretty fine. It's not crushed rock, it's not waste rock, it's not crushed gravel. And there were no lime solids on it. There was no structure at all for that material. So then we took the solids that came off and pulled some samples, a few buckets of water from the drain, line that's draining up here in this area. We ran it through the AM technology, advanced utilization, that's the electrical one. And this is where the solids are maturing and getting ready to precipitate. We then poured it off into our, what we call beer bong, which is the decanting solids. We took the solids off the bottom. Normally, we would take these solids, and our process would include a rotating disc screw press instead of a centrifuge, or you're looking at filter bags, but this is a lower energy, higher solids used. We ended up, because we didn't have that piece of equipment, we just air dried it. And that was what we got chucked and that was the sludge that came off of that. So then, we did pack cylinders on it and we sent those off. I had some leftover material, so I thought, well, if this stuff would be placed somewhere, say on a repository, what's the best way to get it so it stays in place? So it's got string, put it down, you can pack it over over so it's tight. Keep the air out, keep water from it, and get some strength. And I didn't have a roller, so I just took a Tupperware and smashed it down on the bottom of the Tupperware container. And that's what we got after 2 days. Again, I had to scramble to do this presentation because the other data we had from the other facility couldn't present. But this is from that site right here, the sample. And look at some of the samples real quick. And then here's a comparison on the strength. Again, we use formula type 1, type 2 at 20. We use 20 all the way through here. And we did 2 the same, we duplicated it. And again, after 7 days, we had 820 and 710 duplicates. And then we had to calculate it, which typical is you get 65% of your strength in a 7-day cure if it's concrete. So I just tried 0.65. So that's projected. I didn't have enough material to fill up enough cylinders to do the full test. And then we took the fluvial tailings and we mixed those, that's the Eureka fluvial tailings, and we mixed those with those same advanced utilization solids in the same dose. And we ended up at 1240. And again, 50-50 blend. The tailings had a little more structure than the AM solids. And we just had enough for a 7-day break. So we calculated to be 1908. We did have enough left over for one other sample of that material, which we just poured in and just packed everything. Here's the sample of material if you want to see it. We are exposing this to AMD and to acid waters to see how it holds up for strength, but also for leachability balance. So that's the kitty mat. This is before that's whole conditions no longer possible, so that's good.
Sorry, I was trying to help you out.
This is the fluvial tailings before last year's winter and this spring's breakup. We did run that through MBT treatment as we did all the others. That had pretty hot lead, 10,000 total, magnitude of 47. Had 202 TCLP lead level in it. And if that material were to be exempt or lose its exemption under the level, it would be hazardous waste and would have to be treated by LDIs. So we were doing a treatability study on that material, and we were that's all that with MBT. So we took that material and the stuff we just saw from the kitty mat, and that was there's lime salads, that's kitty mat tailings, and that's where we went. We did some blending tests earlier, showing what the material looked like, and that's a 1-to-2 ratio, 1-to-5, 1-to-1 of kitty mat to lime salad. That was an earlier study. Here's a pounded cylinder, and here's a couple samples. Again, that we just had remnants. We didn't have a whole lot of material to work with, and we didn't have a whole lot of money for a lot of testing, but it's what we just generated today. And that's after 30 days. The strength test on it was, I think yourself familiar is 720, but that was the pattern. And that's the sample we showed. And again, here we got some pretty good numbers. 10%, 12% with the dose rate. 7 days, 940, 1790 with a 2% more dose. So this is a cost issue. 2% more cost gives you that much more strength. That's a good thing. But maybe you don't even need to have that kind of strength. Again, we calculated it. Some of the work we're doing right now, an expansion of what we're doing, we have to do it on this material. Freeze-thaw, from a visual perspective, we passed that. On a wet dry, we look okay there. Again, this is visual, we haven't done any testing on it. We do believe that looking at some of these samples that we can get this to meet a 10 to the minus 7 hydraulic conductivity, which is what's desired for caps and covers or liners. Again, we talked a little bit about yesterday, person concrete does crack, but if it was used as a line block, it's sealed right up tight. We're also looking at structural strength in certain construction uses. Without reinforcement, you can put rebar in, or you can actually maybe work from the geotech side of that, where you stretch the tape in there and tension that so you address structural movements. And we're looking to do some on-site scale processing.
I'll get you.
Okay, thanks. Some of the applications were considered. And again, these materials contain total metals. They don't leach, but the metals are still there. That's what it said this morning, this afternoon. They're not going anywhere unless they're moving. So they don't leach, and they're not going to move physically. But I would keep, if you were to use this material on this type of a site, I would keep it with a super pump site or with high levels of metals. But if you use it for road improvements, work pads, surfaces, you use it for armoring or slopes, erosion ditches, channels. We're looking at the burn slope stabilization dams elsewhere, but it would be applied here. Again, that's up to the engineering firm and the group. Figure out lots of ways to use this stuff. Vaults, you make vaults and chambers. Barriers, ecology lines, retaining walls, cross members. I really think Mineville is a good idea. It reminds me of might stop the water, but that's going to take a cultural shift down the road, I think, for a while for that to happen. And make sure that it's not environmental. And then also anti-flow control, because it's not going to reach in good stable water conditions. Some ways MBT can be applied. Similar to technology, we've used made C-camp tile walls with heat drill rigs and drill bits. We've used it on a low scale with plug mills and valley system, or a lime silo, cement silo type reviews during filling and digging into the surface material. This is one we think has got a high application rate in another area we're looking at. Self-propelled, little 10-yard mixer, it can be fixed for small 10, 100-yard quantities, and you can walk somewhere else and get some more materials. And then this is one that we're looking at right here for small application. We got to make sure we're actually looking at some of this for drill kinds and tailors for another project. Some applications, again, this is just off the internet. This is about, but just want to get people to use it for vaults, soldier fire walls, ecology blocks. Being up in the Northwest in Washington, we do a lot of work in Alaska. And one of the things Army Corps does, contractor used to work with Cambridge and Seattle area, made dolos, like, remember the old game jacks? Well, these are tall. Each leg of that is probably 10 or 12 foot tall. And they stack these things up along Aleutian Islands to keep massive soil erosion. They actually fill in the material behind it and they become the stabilized surface. And they're actually using some of these on the upper edge of the river in Washington State from Cascades because of some of the massive glacier melting that's happened up out of North Acre. But that really does control water flow. They move and joggle so it absorbs the energy and then fill comes in and reestablishes. Surface application, another type of retaining wall with drainage, structural members, and another retention wall. Just application possibilities. So there's lots of alternatives to treating acid mine drainage besides lime. Lime preserves sulfides, and at some point, if they get acidified, bacteria in water lose its strength. Metals are insoluble. Somebody mentioned the other day, I think it was Stephen Cook, was talking about circle not fitting very well into mining situations, Superfund sites. But REFRA does, and REFRA was written, and there was something called the bevel amendment, which he used with congressional support from the mining industry to make sure that large quantities of materials don't have to be treated or fall under the REFRA requirements for toxicity or hazardous waste. But that bevel amendment can go away if that material isn't handled properly. And if it does go away, and you lose the exemption, then treatment is required under the law. So that does address mining if the bevel amendment goes away. And then I'm going to digress or change a little bit. There are reputable contractors out there that will work on a public-private partnership, design, build, GCCM type contracting mechanisms that would apply technologies such as some of these see here today and over the last couple events here. It would take the whole risk of treating material. They would take the risk and treat it on a per ton basis or per gallon basis. And if it didn't work, it was a bond, it was a reputation, they won't get paid. So they're willing to take that. They'll take that risk. So yes, it's important to understand the need to know how technologies work. I'm curious, and I had that same curiosity. There's a lot of things going on in our technology we don't know about. But we do know that we had certain objectives, which are the bars that I've heard here through the years since 2015. But that's another way to look at addressing risk of new technology is put it in the contract where it's real, it involves dollars, schedule, time, reputation, and that gets people real serious. So, being the last one speaking today before the full year, adaptive management practices, I would expand that to include specifications that are performance-oriented, where meet this bar and you get paid, or build the way I tell you to build. Let the contractor take the risk. There's some brilliant ones out there that are very well financed, long time experience, but they're willing to do that. And then it speeds things up immensely, especially under certain EPA types of contracts, including when I used to work under back in the day in Chicago, was called PCOPs, Pre-Qualified Operator Procurement System, where contractors of good technologies or technology vendors got pre-qualified. and then a bid came out throughout the EPA's procurement system where you already already used it, where you're already pre-qualified. All you have to do is meet their objectives, submit the price, submit the bond, and you're okay, you got work. Demonstrated success. I understand that, but that's another silo or barrier. It's a fully engineered specification. I understand where engineers and consultants are very scared about putting their PE and PG on the line without understanding the technology. But going through these hoops is another roadblock or at least bump in the road to getting new technology out there. So make sure we have a good understanding of what demonstrated success means. And then, again, I see the water scarcity in the Southwest. I agree with everybody else who mentioned it. It's a huge resource for this valley, and there's people buy water all over the state, all over the country. Southern California. They're paying for water now. And they're paying for it to be clean. And they don't care whether it came from the Superfund side or an active mine or inactive mine. There's cobalt, there's manganese, there's zinc in that water. I don't want to, they can get it out. They don't care where it comes from. It doesn't matter to them. I think that's it. So I'm going to bounce it back to you, and I think last answer to that. How low do you want the metals to be released from it, and what strength do you want, or not? I need to know that, and I give you a number. 20 minutes. Oh, I'm getting the total metals, and I would not recommend you take them off the family inside of the mine site. I mean, somebody might be willing to take that risk, I should, but that's, I can see it being very useful here.
But you could use it, but I do think you are proposing that you could use those a lot similar to the ones that on Contender 6 for retaining.
Yeah, that's right, I was thinking, you're thinking like pavers and walkways, and, I mean, you'd have to look at the total metals, and maybe it's a material that doesn't have high metals content, but it had a lot of sulfide, maybe that's something that would be useful for off-site use. I do have samples if anyone wants to come see some of the products.
Awesome stuff. Well, Karl will be around for more questions if you want to follow up with him. Let's thank Karl for